This video is about Spearman's rank correlation. It's an alternative method of working out correlation between two sets of data. Instead of using the actual data values itself, what happens is you rank both lists from biggest to smallest, and then you work with those ranks. In a minute we'll go through an example. I'll just give you the formula first of all. For correlation, again, we use R, but for Spearman's one we have an R with a little s down there, just to signify it's Spearman's correlation coefficient, not the product moment one. And the formula is 1 take away 6 sigma d squared over n, and then in bracket n squared minus 1. So it's 1 minus 6 sigma d squared, and this bit over here is divided by n into n squared minus 1. The d stands for the difference of the ranks, and that will become clear when we look at an example. So we're going to look at the same example, I think it is, that we used earlier. Here we go, we've got X data and we have Y data. Now, for this method of working it out, you need to rank your data. So if you just look at the X column first of all, the smallest value we have there, you'll see, is 2. The biggest value we have is 19. Now it doesn't matter whether you start these numbers down here are the total. I'll just move those off the screen a minute, we're not going to use those. It doesn't matter whether you start with the biggest number first or the smallest number first. But you need to rank your X numbers. Now I've ranked over here, if you have a look. I've started with the biggest number. The biggest number in this X column was 19, so I've given that a rank of 1. The next biggest number in that column is 14, so that has a rank of 2. The next biggest number is 13, but it's there twice. So 13, well, if there are two values there, in theory they would have rank 3 and rank 4. But because they're the same, you average these numbers over here. So actually we'll give both of them rank 3.5. Then if I go down below 13, the next number I would come to is 7. Now I've used 3 and 4 effectively in these two 3.5, so the next value will have a rank of 5. The next one down is here and here, so this would have a rank of 6 and 7, but because they're both the same, they actually have ranks 6.5 and 6.5. So the next number should have a rank of 8, and that will be the 5, and then a rank of 9, and then a rank of 10. Now because I started rank 1 being the biggest for the X, I do need to make sure I do the same thing for the Y. If I give a rank of 1 for the biggest X, 1 has to be for the biggest Y. You can't mix them over partway through a question. So look at my Y values. The biggest value there is 20, that will have a rank of 1. And here you can see I've ranked all of my Y values. And again, I had some ties. There were two 10s in there. They would have been rank 5 and rank 6. And the average of 5 and 6 is 5.5. So they've both got rank 5.5. So you rank your X numbers, you rank your Y numbers. And then you work out the difference in their ranks. So the difference between 10 and 5.5 is 4.5. The difference between 6.5 and 3 is 3.5. So that's the D number, the D for difference. You just find the difference between the ranks on each row. And then the formula we had earlier had a D squared in it, so each of those differences you square. So 4 squared is 20.25, 3.5 squared is 12.25, and then you have virtually everything you need for your formula. The formula we had was 1 minus 6 lots of the total of the D squareds, and then divided by n into n squared minus 1. So what I need to do now from my table is add up my D squareds. And I've added up my D squareds in this case, and I got a value of 62. So my sigma D squared is 62. You times it by 6, you divide it by n times by n squared minus 1, and n is the number of pairs of data, so here that's 10. So I've put that in. It's 6 lots of the total of 62. N was 10. N squared minus 1 is 10 squared minus 1. That's 99. So that's the 990. Put it in the calculator and you get a value out. Now when we did the same example using the product moment correlation coefficient, we got a value of 0.678. This time we got a value of 0.624. They do give you different values, but they will usually be in the same sort of ballpark area, and you can make a judgment on whether it's strong or weak really by comparing two. If you had two sets of data and you did the Spearman rank on both of them, obviously the one with a value closer to -1 or to +1 would have a stronger correlation than one that had a value closer to 0.